Dear students, in this module we will learn about the applications of energy profile diagram, especially effect of catalyst on a chemical reaction, steric assistance and steric hindrance, thermodynamically and kinetically stable and favorable systems, and limitation of a energy profile diagram. Now let's start from the application part of the energy profile diagram. Almost all factors that affect a chemical reaction and conclusion drawn can be shown by use of energy profile diagram. Here are some selected applications. First application is finding out a kinetic or thermodynamic stable system. As we know, stability is a comparative term. A chemical reaction can only proceed if the free energy change of the system is negative. That is, free energy of product should be lower than that of the value of the free energy of the reactant. If a reaction is proceeded like this only, then we call reaction is feasible. So here we had shown two diagrams. In first diagram you can see free energy of product is higher than that of the reactant, and therefore overall change in free energy, that is free energy of product minus free energy of reactant, would be positive. Product B is having higher energy than that of the product A. It means free energy of product B is have higher value than the free energy of the reactant. So difference of free energy of product minus free energy of reactant would be positive, and therefore this reaction is non-spontaneous, that is not feasible. While in the second diagram you can see if the reaction is going from B to A, you can see free energy of A is lower than that of the free energy of B. Here B is a reactant, and therefore reaction from B to A is feasible, that is spontaneous, because free energy change of the system is negative. At the same time, if enthalpy of the product is less than that of the reactant, then the product is called thermodynamically stable. When we plot energy profile diagram, that is when we plot a diagram between reaction coordinates and enthalpy of the reaction, the energy of product B is higher than product A, than reactant A, then the reaction is called thermodynamically less stable. While when the same reaction undergoes from B to A, then enthalpy change is negative, and we call the reaction is thermodynamically form stable product. On the other hand, even if your reaction is feasible, product is thermodynamically stable than the reactant, but your reaction may not proceed just because of requirement of very high activation barrier and cannot be practically reached. Such reactions are called kinetically unstable. So the same we can show by the diagram. So on comparison we can say that thermodynamic stability of product depends on energy of reactant and product, while kinetic stability is completely dependent on the activation barrier. So you can understand here that enthalpy or free energy of the system is a state function only, and it doesn't depend on the followed path. while activation barrier depends on the path of the reaction. Therefore, when we call about thermodynamic stability, in which we compare energy of reactants and product only, are state dependent, while kinetic stability, where we talk about the activation barrier, is path dependent. In some cases, a reactant may have possibility to form two parallel products. As like reaction, energy profile diagram for both the reaction will be different. You can understand this because for the formation of both the product, the path will be different. So, the formation of energy profile diagram will also differ. So, let's imagine a situation in which from reactant we produce two different type of product, that is product first, which is shown in the left side of the diagram, and product second shown in the right side of the diagram. In the two cases, you can see when product first is forming, the energy of product first is very lower than that of the reactant. So, the product that will form here will have higher stability. Also, if you see the right side of the diagram, product second is also having lower energy than that of the reactant. But if we compare the two reaction, and as we know, stability is a comparative term, when we compare the two reaction, product first comparatively very less energy, while product second is having higher energy compared to product first. So, product first here is a thermodynamically stable product, while product second is thermodynamically less stable. Means from path 1, that is reaction in which product first is forming, is thermodynamically favorable than that of the product 2. Now, if you compare the activation barrier of two paths, you can see reaction second needs lower activation barrier for proceeding of a reaction than that of the reaction first. So, reaction second will form more activated complex than that of reaction first. So, overall product second is kinetically favorable, while formation of product first is thermodynamically favorable. Since stability is comparative term, we can say product first is thermodynamically more stable than product second. With the same set of information by energy profile diagram, one can conclude product second is kinetically stable than that of product first. So, at lower temperature, kinetic factor will dominate because more number of activated complex will be formed for the formation of product second. But at the same time, chances of reversibility of reaction will also high, because in the backward direction requirement of activation energy is also low. At higher temperature, formation of both the product is favorable because a good number of activated complex for both the reaction may form, but chances of reversibility of reaction is very less in case of formation of product first, because with the existing energy of the molecule, product second can cross activation barrier easily to reform reactant, but reversibility is difficult with product in case of reaction first. Therefore, with the completion of reaction at higher temperature, product first dominates over product second. Now, we go towards the second application of energy profile diagram, and this is the effect of catalyst in a chemical reaction. A catalyst is a substance which has a rate of a chemical reaction without altering itself. The enhancement of rate of reaction can be correlated with the number of activated complex that forms in a particular reaction. It means a catalyst can provide a path through which more molecule of reactant can form the activated complex. In other words, catalyst can provide a new path for a chemical reaction that has lower requirement of activation energy. It is also worthy to include here that a catalyst cannot change reactant or product including their energy levels. All these explanations can be diagrammatically represented through energy profile diagram, which is shown here. So in the diagram you can see, without presence of a catalyst, a reactant needs higher activation energy to reach towards transition state, and only after reaching this transition state or after crossing this activation barrier, product can form. But if we supply a catalyst, catalyst provides a different pathway for the reaction which do not change energy of reactant and product. Even it doesn't change itself, but it provides a new path which requires lower activation barrier, as a result of which more number of activated complex form at the same temperature and reaction will be faster. Now let's go towards the third application called steric hindrance and steric assistance. With crowding of electronic field of ligands, energy of system increases because of inward repulsion between them. These crowding may either assist a reaction or may hinder a chemical reaction. For example, in SN1 reaction, bond breaking is the rate determining step. So in case of a bulkier ligand, energy of reactants will be comparatively higher, and therefore the molecule or reactant needs a small activation energy to reach towards the activation barrier. While in case of SN2 reaction, nucleophile attacks from rear end of leaving group, which increases the crowding in the transition state. Means activated complex is more crowded than that of the reactant, and therefore in case of bulkier ligand, energy of transition state will increase, that result increase of activation barrier. So wherever substrate has choice or chance to undergo SN1 or SN2 reaction, substrate with bulkier ligand will prefer SN1 reaction and vice versa. A representative energy profile diagram for SN2 reaction with lower requirement of activation barrier and higher requirement of activation barrier is shown here. Note that above diagram is manipulative for making a convincing model to the students in practice. Reactants and product in both the diagrams are different, and therefore their energy will also differ. The two diagrams represent two different reactions. We learned different applications of energy profile diagram, but it has a major limitation. The changes in the reaction coordinates are associated with degree of freedoms. Monitoring a single degree of freedom cannot provide exact relation of reaction coordinates with energy of reactants. For example, you can understand that if a reactant is having 3 atoms only, then total number of degree of freedom would be 3 into 3, 9. If you subtract translational and rotational degree of freedom from there, then it would be either 4 or 3. For example, in case of CO2, total number of vibrational degree of freedom would be 9 minus 3 translational degree of freedom and 2 rotational degree of freedom, which makes an overall 4 vibrational degree of freedom. So in order to see entire change in a reactant, we need to plot an energy profile diagram between energy and all 4 vibrational degree of freedom together, which will result an energy profile diagram 5-dimensional, which is not only difficult to understand but is difficult to plot. With increase in number of atoms in a molecule, vibrational degree of freedom will also increase, which will enhance complexity in the diagram. So practically, this theory is applicable for 2 atom molecules only, where vibrational degree of freedom is only 1, that result a 2-dimensional energy profile diagram. Now let's summarize the whole learning. Energy profile diagram is capable of showing entire reaction by plotting energy versus reaction coordinate. A catalyst provides a different path of a chemical reaction which lower activation energy but do not change initial and final state of a reaction. The crowding of substrate may either support or oppose proceeding of a chemical reaction. If a reaction becomes faster because of crowding, then we call the procedure as steric assistance, while if it hinders a proceeding of a chemical reaction, then it is called steric hindrance. Reaction products are thermodynamically stable if its energy is lower than that of reactant. Reaction will be kinetically stable if activation barrier of the reaction is lower. In a parallel reaction, product having lower activation energy will be kinetically favorable and will give better yield at lower temperature, while products having lowest energy value will be thermodynamically favorable and produce better yield at higher temperature.